let's now talk about ideal gases. Here is the ideal gas law that we introduced in introductory chemistry, which we've now relabeled equation of state. That's the name for that. There are 4 state variables here: pressure, volume, number of moles, and temperature. And if you specify 3 of the 4, the 4th is specified by the equation of state. And this tells the relationship between the variables when the system is at equilibrium. Also in introductory chemistry, we talked about the kinetic molecular theory, and there we found that the kinetic energy was 3/2 RT. Let me rewrite this as this way. Kinetic energy was 3/2 nRT. So in this case, this would be the kinetic energy per mole. That would be the intensive variable. But if you have n moles, this would be the kinetic energy, which is the extensive variable kinetic energy, 3/2 nRT. What we're going to show is that, or we're going to argue, that in fact the internal energy of an ideal gas is just equal to the kinetic energy. And again, I write the extensive version of this. Ke is 3/2 nRT. And we're also going to find that the heat capacity is, for an ideal gas, is equal to 3/2 nR, heat capacity at constant volume. And the heat capacity at constant pressure is the heat capacity at constant volume plus R. So that's what we're up to. First, let's talk about the equation of state of an ideal gas and the kinetic molecular theory. Now, recall the kinetic molecular theory, what we had was a container, 3-dimensional container, and within this we had a model of gas molecules. These were incompressible spheres whose volume was equal to 0, and they were in random motion. And as these molecules would strike the sides of the container, they would transfer momentum. Even though their volume is 0 in the kinetic molecular theory, they nonetheless have mass. So as the momentum of the moving gas molecule would be transferred to the sides of the container, that would give rise to pressure. And we showed in introductory chemistry that kinetic energy is, for n moles, is 3/2 nRT. Now what I want to argue is that this kinetic energy is in fact the internal energy in the kinetic molecular theory. In the kinetic molecular theory, the only energy that these gas molecules have is the kinetic energy. If that's the only energy, then the total internal energy of the gas molecules would just be equal to the kinetic energy. And then if we look at, say, how U changes with temperature at constant volume, and that's defined as the heat capacity at constant volume, this then would just be 3/2 nR, or if you want to convert heat capacity from an extensive to an intensive variable, divide by the number of moles, CV over N, which I think Ball uses maybe CVM for molar heat capacity, and that's equal to 3/2 R. So I hope I convinced you that the internal energy of an ideal gas is just the kinetic energy, which is 3/2 nR, and the heat capacity of an ideal gas is just 3/2 nR, or the molar heat capacity is 3/2 R. So I hope I've convinced you that.